Before watching this lecture, you need to understand how powers with exponents that are not integers are defined. For example, you need to know what we mean by 10 to the 0.25. Let's begin this lecture by looking at powers with base 10 for various exponents n. If n is 1, then the power 10 to the 1 is 10. Increasing n to 2, and the power will be equal to 10 to the 2, which is 100. n equal to 3 gives us 10 to the 3 or 1000 and so on. We have created a map from n to the power 10 to the n. n equal to 1 is mapped to 10, n equal to 2 is mapped to 100, and so on. We can create a map that is the inverse or backwards of exponentiation. That is, we map 10 to 1, 100 to 2, 1000 to 3, and 10,000 to 4. The inverse mapping is quite straightforward. We simply count the number of zeros. The inverse of exponentiation when the base is 10 is called the common logarithm. We write log followed by 10 to denote the common logarithm of 10, and as we demonstrated, this is equal to 1. Similarly, the common logarithm of 100 is 2. 100 has 2 zeros, which means that it can be written as 10 to the 2. The common logarithm of 1000 is 3, and so on. Let's extend this idea to negative exponents and the exponent 0. First, if n is equal to 0, then we have 10 to the 0, which is defined as the number 1. Therefore, the common logarithm of 1 is the common logarithm of 10 to the 0, which is defined as 0. We can also allow exponents to be negative. If n is equal to minus 1, then we have 10 to the minus 1, which is defined as 1 divided by 10 to the 1, or 0.1. Therefore, the common logarithm of 0.1 is defined as minus 1. Similarly, for n is equal to minus 2, 10 to the minus 2 is 0.01, and the common logarithm of 0.01 is minus 2. Let's look at powers with base 10, but where the exponent can be any real number. I will write it as 10 to the a when I allow a to be a non-integer. For a equal to 0, 10 to the 0 is 1, and the common logarithm of 1 is 0. When a is 1, 10 to the 1 is 10, and the common logarithm of 10 is 1. Let's pick a value for a in between 0 and 1, say 0.5. 10 to the 0.5 is the same thing as the square root of 10, which is 3.162. Therefore, the common logarithm of 3.162 is 0.5. To illustrate what we have done so far, let's do a real line for the exponent and consider numbers between 0 and 1. The exponent can be mapped to the power 10 to the a. Let's use the name c to represent 10 to the a. A equal to 0 is mapped to c equal to 1. A equal to 1 is mapped to c equal to 10. And a is equal to 0.5 is mapped to c equal to 3.162. An arrow pointing upwards means exponentiation 10 to the a. The common logarithm is the inverse of exponentiation, and it can be illustrated with an arrow pointing downwards. A equal to log c. We can add a few more points to this picture. 10 to the 0.25 or 10 raised to 1 over 4 is equal to 1.778. 10 to the 0.75 is equal to 5.623. And the common logarithm of 5.623 is equal to 0.75. The point now is that as I keep on filling out the lower real line with numbers between 0 and 1, I will fill out the upper real line with numbers between 1 and 10. This means that for every real number between 1 and 10 on the upper real line, there is a corresponding real number between 0 and 1 on the lower real line. This also means that the common logarithm of any number between 1 and 10 exists, and it's a number between 0 and 1. If you need to find the common logarithm of an arbitrary number between 1 and 10, say log of 7, our picture reveals that it must be between 0.75 and 1. You could find the answer by trial and error. For example, if you try 10 to the 0.85, you get 7.079, thus the common logarithm of 7 is slightly below 0.85. Fortunately, there is no need for this trial and error process. The common logarithm has been programmed into most calculators. To find the common logarithm of 7, we simply do 7 and then we click the log button. We find that the common logarithm of 7 is 0.845. That also means that 10 raised to 0.845 must be equal to 7. Remember how the arrows go up and down. Clicking 10 to the x, we can confirm that this is true. Exactly the same idea applies if we extend those two real lines past 1 and 10. We can do exponents 2, 3, and 4, and so on, and powers 100, 1000, and 10,000, and so on. For example, the common logarithm of 500 must be between 2 and 3. If I calculate 10 to the 2.7, I get 501.2, which tells me that the common logarithm of 500 is slightly below 2.7. The exact value is this number, 2.699, and so on. We can also extend these two real lines to the left. We can do exponents -1, -2, -3, and so on, and powers 0.1, 0.01, 0.001, and so on. For example, the common logarithm of 0.005 is between -2 and -3. 10 to the -2.3 is slightly above 0.005, and the common logarithm of 0.005 must be slightly less than -2.3. This is the exact answer. We have now illustrated how the common logarithm of any number c greater than 0 is defined. The starting point is that the equation 10 to the a equal to c always has a unique solution. Therefore, c can always be written as 10 to the a for some unique number a. The common logarithm of c is then precisely a. Sometimes we drop the word common if it's clear from the context that the logarithm we're using is the common one. The logarithm of 100 is equal to 2 since 100 can be written as 10 to the 2, so that when c is equal to 100, a is equal to 2. Similarly, log of 0.01 is -2 since 0.01 is the same as 10 to the -2. This explains why you cannot find the common logarithm of 0. 0 cannot be written as 10 to the a for any number a, since 10 to the a is always strictly positive. The same is true for the common logarithm of negative numbers. They do not exist. A negative number b can never be written as 10 to the a, no matter how we pick a. The logarithm of 0 and the logarithm of negative numbers are not defined, at least not as a real number.